Hello everyone, my name is Salman and very recently I started my online educational platform. We are going to discuss a topic in physics. In fact, it's not a topic, it's a concept, and the name is frame of reference. So let's learn about frame of reference. Frame of reference is an extremely important topic in physics, and it is normally discussed in the starting of physics in intermediate classes. And unfortunately, some of the students skip this topic considering that it is not that important, but I'm telling you it's very, very important. So please listen very carefully. And once again, I am reiterating it's extremely important. You will find its application at many places, right? So let's start knowing about frame of reference. So if we go by the definition in dictionary, please don't get scared. I'm not teaching you literature. I'm restricting myself to physics only, because when I talk about dictionary definition, you may think like that. So dictionary definition goes like that: a particular set of beliefs, ideas, or experiences that affects how a person understands or judges something. So a set of beliefs which a person develops in an environment, the ideas and experiences which has a bearing on his understanding and judgment. Let me give you an example. Suppose your upbringing is in an environment where people are extremely strict. So you will also start thinking on those lines. You will have probably a very, very strict kind of behavior, a no nonsense approach you will develop. You'll not tolerate a small deviation also. But if your upbringing is in an environment where people are a bit lenient, so your thinking will be a bit different. So your thinking or your judgment or your judging people, it depends upon the environment in which you have been brought up. So environment plays an important role. So there is a correlation here with physics also. Once we discuss in detail in this chapter, you will come to know about that. Let's now shift our focus slowly to physics. In this snap, you can see a very, very tall structure. At time, it was the world's tallest building, Empire State Building. But now it's not the tallest. There are other buildings which are even taller than that. But if you stand in front of that, and you will look at with an astonishment how tall it is, right? But if you watch the same structure through a window while sitting in a plane, you will not have that kind of feeling what you have when you are standing in front of the building. Now here you are watching through a window of a plane, of an aircraft, and you are seeing a very small size, compared to the actual size. But if a plane is at an even higher altitude, the size will even be smaller, and probably at some altitude you may not even notice that you are seeing the same thing. So you are seeing the same thing in different environments, and your feelings, your reading about the things are different. Now let's talk about the definition of frame of reference. It's a system with respect to which position and time coordinates of an object or an event can be described. Like, for example, this is an object P. Now, position of any point or an object P at any given time can be expressed in terms of x, y, and z coordinates, taking some frame of reference. Like, you take these set of axes and at any point, any time, you express its position in terms of x, y, and z. So this is a frame of reference, right? There can be any number of frame of reference by which you can express, the coordinates of P at a given time t. Now, if an observer is in different frame of reference, the same thing will be observed differently by him. Let me give some example. Now we consider the cases below. Case 1. If my frame of reference, that means observer, is on the ground, say this is the ground, and this is the observer. So observer, or you can say frame of reference, is on the ground. There is a car which is moving towards observer with a speed of 100 km per hour, and there is an aircraft which is flying in the sky away from the observer with a speed of 500 km per hour. So for the observer on the ground, car will be moving towards him with a speed of 100 km per hour, and plane will be moving away from him with a speed of 500 km per hour, right? Now my observer is in a different frame of reference. Like, frame of reference for the same example, frame of reference is shifted to the car. Now my observer is inside the car. Now what will happen for the observer inside the car? Car will appear to be stationary, first of all, until and unless he sees out of the car. If he is in the car and he is not observing outside, so it will appear that car is stationary until and unless there are some jerks, which we are ruling out here. Now ground appears to be moving towards him with a speed of 100 km per hour. You must have seen when you are driving in a car, the trees appear to be moving towards you. And the plane which is moving towards the observer, it will appear to move with a velocity of 500 plus 100, that is equal to 600 km per hour. So plane appears to move towards him with a speed of 600 km per hour. Case 3. Frame of reference is inside the plane. Now my observer is sitting inside the plane. What will happen for the observer inside the plane? So plane will appear to be stationary until and unless he sees out of the window. You must have experience while traveling in a plane. If you don't see outside, it looks that plane is stationary. So plane appears to be stationary. The ground appears to be moving towards the observer with a speed of 500 km per hour, and the car appears to move towards him with a speed of 500 plus 100, that is equal to 600 km per hour, right? Here, we are considering the altitude of the plane is not very high. Otherwise, if it's very high in the air, the speed of car will be a bit insignificant, but it's quite close. Here we are assuming the distance between the plane and the car is not, very large. So we have seen in all these 3 cases, the physical quantity has different values when measured by observers in different frame of reference. When an observer was on the ground, the car was moving with a speed of 100 kilometers towards him, and plane going away with a speed of 500 kilometers per hour. When observer is shifted to car, the same quantities have different values, and when the observer is in a plane, the same quantities have different values. So the frame of reference are primarily of two types. One is inertial, the other is non-inertial. What is inertial frame of reference? In case of inertial frame of reference, the Newton's law correctly describe motion of a body. Such frames are either at rest or they are moving with a uniform velocity. So what are non-inertial frame of reference? Here Newton's law does not hold good. In fact, they are not able to correctly describe the motion of a body. Such frames are either accelerated or rotating. See the difference. Inertial are at rest or uniform velocity, but non-inertial are accelerated or rotating. If we want to make Newton's law hold good, then we have to consider some mysterious force called pseudo force. So it's not that Newton's law does not hold good. Actually, they do not hold good for the observer inside this frame of reference. In this non-inertial frame of reference, it will appear that Newton's laws are being violated because the person who is sitting inside this frame of reference, he doesn't see outside. So for him, Newton's laws are being violated. They seem to be violated. But a person who is seeing the picture in totality from outside this non-inertial frame of reference, for him, Newton's laws are perfectly applicable. Anyway, some examples will make it absolutely clear. Now we'll talk about inertial frame of reference. An observer is sitting inside a train, observes a bob hanging from a ceiling of a train when train is either at rest or it is moving with a constant velocity v. Say train is at rest. Observer is inside the train. He sees the bob is hanging and there is no movement. Since there is no apparent force, he doesn't observe any force on that. So it is at rest. So Newton's law holds good. Without a force, there is no movement. Now train is moving with a constant velocity. Then also the bob is hanging in the same position. So in both the cases, observer finds no change in position of bob as there is no force. So it implies that Newton's law is holding good. There is no force. There is no movement. Because Newton's first law says that every body continues to be in its state of rest or of uniform motion until and unless there is some external force. Here the observer sees no external force. So what is that rest? Both these are examples of inertial frame of reference. You can see that in one case, in the first case, frame of reference is at rest, means observer is at rest. In the next case, it is moving with a uniform velocity. That's what we discussed few minutes back. Okay. Now let's discuss non-inertial frame of reference. Now the train which is moving with a constant velocity suddenly accelerates or decelerates, and we observe that position of the bob changes. However, the observer inside the train does not see any force. Like if the train suddenly accelerates, what will happen? The bob will go backwards, will move backwards. So observer sees, array, there is no force. Still, it's moving backwards. Now here you may get a bit, confused that when we are sitting inside the train and train is accelerating, we feel that no, the train is it's so big that you don't feel the acceleration, what is happening outside. Or instead of observer, I say there is a camera here, and you are seeing the position of that bob from a remote place through a camera. So you don't know whether the train is accelerating or decelerating. You just see that there is no apparent cause and the bob has moved backwards, right? Or if the driver suddenly applies the brake, what will happen? There will be a retardation and the bob will move forward. Here also observer sees that there is no, apparently he doesn't see any force because he cannot see outside the train. So he sees there is a motion in the bob without any force. So he feels that Newton's law is violated. However, an observer which is outside the train, he sees that the train is accelerating or there is a retardation. So for him, the Newton's laws are applicable perfectly fine. But for the observer inside the train, it appears that these laws are being violated. So both these cases are non-inertial frame of reference. They are examples of non-inertial frame of reference. We'll consider one more example. A coin is placed on a rotating disc, and an observer sitting on the disc sees that position of the coin changes. Now this is a disc which is rotating, and an observer is sitting on the disc. A disc is too big for an observer to feel that it is rotating. For example, let me give you an example. We all are inside our planet Earth, which is rotating, and around its axis. But do you feel it? No, so big you can't feel it. But you are in continuous motion. So an observer is sitting on the disc, and a coin is placed here. Now the coin is not anchored to that place. What will happen? After a certain time, the coin is free to move. This is a smooth disc. What will happen? This is the initial position of the coin. After some time, the coin will follow this kind of trajectory. This is the path of the coin, and you will find the coin at this place. Here also, observer doesn't see any apparent force. He sees there is no force. Still, the coin has moved from this place to this place. So he feels that Newton's law is being violated. But an observer which is sitting outside the disc, when he sees this, he gets the reason why coin has moved from this place to this place, right? So this is also an example of non-inertial frame of reference. So what did we say, a few minutes back, that in case you want Newton's law to hold good, you have to consider a pseudo force, right? So now we'll show you how we consider this pseudo force and what is the direction of pseudo force. In all the three discussed cases of non-inertial frame of reference, if we want validity of Newton's law, so we have to assume a pseudo force. Let's see. Now let's first of all consider, the train case where train is accelerating. Suppose this is the mass of this bob and train is accelerating at a rate of a, right? So because of the inertia, this bob will move like this, but the observer inside the train will not feel this acceleration. He can't see what is outside. So if you want Newton's law to be applicable here, we will assume a pseudo force in opposite direction to this acceleration. That means like this. So pseudo force will be, that force will be m into a. Please note this. It's very important. So pseudo force is in the reverse direction of the acceleration. Now consider another case. Here also, since the train starts retarding, but this bob owing to inertia will try to continue in the same direction. Suppose its mass is m and retardation is with a. So here also you have to consider the pseudo force in the direction opposite. That means if acceleration is in this direction, which we call retardation, the pseudo force will be in this direction, like this, and pseudo force will act as m a in this direction. Consider the third case of the coin. Now here there is an acceleration which is towards the center. We call it centripetal acceleration, which is v square upon r, where v is the linear velocity and r is the, this distance from the center. So centripetal force on the coin will be m v square upon r. So you have to consider the pseudo force in reverse direction. That means pseudo force will be in this direction and its value will be m v square upon r. So there will be a force in this direction away from the center. So since the coin is also moving in circle, it's following a circular path, and at the same time there is a force which is acting away from the center, so it follows the path like this, right? So these three cases make it absolutely clear as to how we consider the pseudo force. Pseudo force is only considered to make Newton's law hold good for the observer which is in this frame of reference, not for the observer who is outside, who sees the picture in totality. So that's what I have discussed, that it's important to note that observers sitting outside the accelerated or decelerated train or rotating disc, there is no violation, and his is inertial frame of reference if he is at rest. However, the frame of reference inside the accelerated or decelerated train or a rotating disk, they are all examples of non-inertial frame of reference. Now, if we consider a frame of reference attached to Earth, do you think it's an inertial frame of reference? Precisely, it is not inertial, because if this is your sun, this is your sun, so Earth follows a kind of elliptical orbit. This is your Earth, and at the same time it rotates about its own axis. So Earth is rotating about its axis. So frame of reference which is attached to Earth is precisely non-inertial frame of reference, and apart from that, its velocity also changes. When it is far from sun, it has lesser speed than when it is closer to sun. You will read this in Kepler's laws of motion. So it is having acceleration also. So from both point of view, because of axial and orbital motions of Earth, it's not precisely an inertial frame of reference, but it can be considered inertial. For all practical purposes, we consider it as inertial frame of reference. Now, if the frame of reference is inertial, then every other frame of reference is very important, which is in uniform motion relative to it, is also inertial. Suppose there is a frame of reference which is inertial, and there is another frame of reference which is either at rest, definitely then it will be inertial, or if it is uniform, it is moving with uniform velocity with relative to this frame of reference, then it is also an inertial frame of reference. Now let's consider few examples which will make this topic even more clear. Consider an observer in a lift, and he is observing a weight placed on a weighing machine. Now this is a weight which is placed on a weighing machine, and this is my observer inside a lift. Now consider a few cases. Lift is stationary. What will happen? Weight of the block will act downwards, mg, if m is the mass of the block. With this, it presses the balance. That means this is the weight by which the block presses the balance. Now balance also has a reaction which is in opposite direction. It exerts equal and opposite reaction, which is on the block, say, which is R. As per Newton's third law, for every action there is an equal and opposite reaction. Now what will happen? Now this reaction will be equal to this W by which it presses the block. So R is equal to W is equal to mg. So observer sees the correct weight of the block. So this is an case of inertial frame of reference. Consider other case. When lift is moving with a constant velocity, like this. Here also, the same thing. Observer sees the correct weight of the block. This is also a case of inertial frame of reference. Third case, lift is moving up with a constant acceleration. Now what will happen? If the observer, for the observer who is outside this whole system, he will see that the block is moving upwards with an acceleration. So if he sees the forces on the block, one is R, one is mg. Net force on the block is upwards, which is ma. So that means R minus mg is equal to ma. That is the net force. So R is equal to mg plus a. Now R is equal to W. So W is equal to mg plus a. That means the block weight will be increased. The weighing machine will show the weight more than the actual weight, mg plus ma, right? This we must have experienced when we are, traveling in a lift and lift start accelerating. We feel a bit heavier. But as per the person in the lift, R should be equal to mg, since as per him the block is at rest. He doesn't see any force. He is not able to see the acceleration of the lift outside. So as per him, R should be equal to mg. But this is wrong. So this is the case of non-inertial frame of reference, because for observer, if he wants Newton's laws to be applicable, he has to assume a pseudo force. So because he sees the weight has increased, so how it has increased? That means there is some force which he is not able to see, which is again acting on the weighing machine, which is responsible for this increase. So pseudo force, we discuss that it will be in reverse direction. That means this is the direction of pseudo force, and its value will be m into a. So now if you apply this pseudo force, R is equal to mg plus ma, right? This is what an observer outside is able to visualize, because he sees the acceleration also. Okay, hope this is clear. Now, if we consider the case that the lift is moving with an acceleration, constant acceleration downwards. So for an observer who is outside, what will happen if he consider only this block? So this block is moving downwards with an acceleration a. That means there is a net force of ma downwards. There is a reaction on the block R. There is a weight mg which acts downwards, and the net force is ma. So that means mg minus r is equal to ma. That means r is equal to mg minus ma, and r is equal to w, the reading of this machine. That means now the reading has decreased, because actual reading should be mg, but it has decreased by ma. But this observer, since he is not able to see the acceleration downwards, he thinks that r should be equal to mg. So this is also case of non-inertial frame of reference. So again, a pseudo force of ma in the reverse direction, which is upwards, has to be applied. That means like this. So pseudo force will be m into a. Now if you see, r plus ma is equal to mg. That means r is equal to mg minus ma. So, and r is equal to w. So reading goes down by ma. Reading is reduced. So for validity of Newton's law, we apply pseudo force in this case in upward direction, and in the earlier case in downward direction. So that's all in frame of reference, and I hope the concept of frame of reference is clear to you. And thanks for watching this. Have a nice day.